So this is it's actually a much nicer sort of sandbox to play in, even though it's a little, chemically, it's a little harder to visualize. So, again, I'm an information theorist, so I like to boil things down to idealized assumptions. So what I want to do is I want to strip away, I don't want to worry about the chemistry because I'm not an expert in the chemistry. What I want to do is I want to strip away all the irrelevant details and come up with a model that I can think about as a mathematical object. So I come up with the following ideal system assumptions. Now this one's totally unrealistic. Transmitter and receiver are perfectly synchronized, but it's very useful. So if you want to talk about timing, it's useful to think of the transmitter and receiver as being synchronized. In other words, they agree on a certain time base, and they can measure time independently with respect to that same base. Secondly, the transmitter perfectly controls the release times and physical states of the transmitted particles. Release times, so obviously if you want to tell the transmitter to, in my binary example before, you want to tell the transmitter to either send a 0 or a 1, you're telling effectively the transmitter to send particular molecules at particular times. You want the transmitter to have perfect control over them. Physical state, what I mean by physical state is if there's any physical state to the Brownian motion other than just release time. In the Wiener process, it's only release time that matters. But if there's any other physical state, you want that controlled as well. Again, the flip side of that is the receiver perfectly measures the arrival time and physical state of any particle crossing the boundary. So these three assumptions, like I say, they're rather unrealistic, but you can see where they're sort of appropriate for an idealized system model. And the last one, this is interesting. The receiver immediately absorbs any particle that crosses the boundary. In other words, in my sodium example, so I drop sodium ions in, the receiver does, they propagate to the receiver. Once the receiver detects that ion, what the receiver does is it measures the arrival time, and it grabs it, and then it's gone. It doesn't propagate anymore. So you can see where that's convenient. What the consequence of ignoring that assumption is kind of like intersymbol interference. So if you observe a sodium ion and then let it go again into the system, and then you see it again, you don't know if that's a new one or one you've already seen before. So what I've been able to prove, and let me, as a background to this, let me explain that the simple act of modeling this channel it's not obvious how to do it. But this is one of my results, which is that for these arguably unrealistic, arguably idealized channel assumptions, it turns out that what you get is the information theoretically interesting consequence that mutual information using those assumptions is higher than if you managed to ignore one of the assumptions. So the trade-off here is that if you ignore any one of my assumptions, you get a more realistic system, but you also know that mutual information will go down. So in other words, the assumptions that I've given you are ideal in the sense that they are maximum mutual information. There's no system that can do better than that if you abandon those assumptions. Okay, so the proof of that statement, 1, 2, and 3, those are obviously ideal. So what I assumed there was synchronization. So obviously if you throw out synchronization, mutual information will go down. 2 and 3 were transmitter and receiver are perfect, basically. So they perfectly measure and perfectly control. The one that's not obvious is number 4, but that's fairly intuitive to show, and it's a property of Brownian motion. So if I release a particle here, it propagates to the receiver, and at the first arrival, the receiver perfectly measures the state of that particle, and then lets it go again. The subsequent path, because the state is perfectly measured here, the subsequent path of the particle is conditionally independent of the earlier path. So in other words, if the receiver tagged this particle once it observed it and then let it go again, it could safely ignore any subsequent arrivals because that particle is tagged, and because it was recorded here, that's sufficient to record all of the information in this previous path. So in other words, it's like a markup chain. Once you observe it here, you don't need to observe it again because you already have all of the information that you need. So that subsequent path can be safely ignored. So in other words, whether it's tagged or removed is the same thing. On the other hand, if you didn't tag, which is what you would do if the particle arrives and you just let it go, you can show by the data processing inequality that you would necessarily have to lose information, so mutual information would go down. So, in other words, the takeaway message there is that the only really important thing that we need to worry about is first hitting time. So in other words, the first time that the molecule arrives at the receiver, that's the only property of Brownian motion that we need to use. So that's really awesome for two reasons. Firstly, the chemical literature is hard, and secondly, the mathematical Brownian motion literature is hard. So by using these idealized assumptions, you can boil it all down to a very small problem of the first hitting time.